We're starting section 2.7, limits at infinity. First, we discuss the graph at infinities in calculating limits at infinity, vertical asymptotes, horizontal asymptotes, roots and infinite limits, and then asymptotes of common functions. So infinity in the input. When this is when limits as x approaches infinity. So limit as x approaches infinity of f of x is equal to L, and the value of f of x can be made as close to L as we would like by taking x sufficiently large. So and here, for example, you can see about this side that as x gets bigger and bigger, I can choose a small positive number, whichever small positive number I want, and there's an x value big enough that y value in there is going to be smaller than that, basically. So you make the x, if you go further along the x-axis, you find a place that all the y value becomes smaller than and become very close to L, basically. L in here is 0. And same thing over here. You see that there are other forms of infinities in here. We discuss them in a couple of pages. One thing is that you don't see the when this infinity is changed to negative infinity, then negative infinity is this side behavior of the function. And then you also see that there are and the y value going to infinity, that those are the vertical asymptotes. And so input in the output, limit as x approaches a of f of x is equal to infinity. That's the values of f of x can be made as large as we want by taking x sufficiently close to a but not equal to a, basically. And so these are the vertical asymptotes. So if you go to very, very small x value, then you can see that at that x value, and the y gets, as x gets smaller and smaller, the y gets bigger. And the discussion is that choose however big y you want it to be, and then you can find the x small enough that that all y values basically with x value closer than that to 0 is going to be bigger than that amount. So you want to make it bigger and bigger after that, basically. Vertical asymptotes. The line x equal to a is a vertical asymptote of the curve y equal to f of x if at least one of the following statements is true. So the vertical asymptote idea that we had from the before now is translated into limits, and that's either limit as x approaches a of f of x is equal to plus minus infinity, or limit as f of x approaches x2 from right side to a is equal to plus minus infinity, or limits as x approaches a from the left side of f of x is equal to plus minus infinity. So either both-sided limits are going to infinity, or one-sided limit is going to infinity. Any of those cases, the vertical asymptote is that's called the vertical asymptote. Vertical asymptote we're very familiar with and is one-sided, as y equal to ln of x has vertical asymptote x equal to 0. And notice that nothing is defined to the left of the y-axis, and the y-axis is the vertical asymptote, and x equal to 0 also not defined as not part of the domain neither. In this case, limit as x approaches 0 is going to be negative infinity. See, the direction goes negative infinity. So a lot of times you want to make the ln of x have the ability to be symmetrical. And so by putting absolute value of x inside the ln, you get a symmetrical way, and all the negative numbers actually can fit in this function also. And so y equal to ln of absolute value of x has the one side like this and a mirror image on the other side. It's not defined for x equal to 0, and this is a two-sided vertical asymptote. What else do we know? Let's say any rational function y equal to a polynomial on top, a polynomial on the bottom is going to have a vertical asymptote if the denominator has a root. And so in the most simplified form, if the function is in the most simplified form and the denominator has a root, basically. And what I say about most simplified form is that if it can be simplified, there would be just a whole, or there might be just a whole and not the vertical asymptote. And so this is another vertical asymptote that we're familiar with. And trig functions, y equal to secant of x has infinitely many vertical asymptotes, and y equal to tangent of x has infinitely many asymptotes. Now let's discuss horizontal asymptote. And the line y equal to L is a horizontal asymptote of the curve y equal to f of x if either limit as x goes to positive infinity of f of x is equal to L, or limit as x approaches negative infinity of f of x is equal to L. Now, in these two come in handy in calculating a lot of limits in this section. Limit as x approaches positive infinity of 1 over xn is equal to 0. If you go back to the first picture, the first graph that we introduced here, we went over 1 over x to power 1 and 1 over x to power 2, and now we're saying that for any n it's true as x goes to positive infinity. If x goes to negative infinity, the exponent this is only defined when exponent has denominators that are odd. 2 over 1 is an acceptable one, for example, but let's say 3 over 2 is not an acceptable denominator for x to power. And so in that case also, limit as x approaches negative infinity of 1 over xn is going to be equal to 0. And this too help us figure out a lot of rational functions. Limit as x goes to plus minus infinity of rational functions, which is a polynomial in the numerator, polynomial in the denominator, is going to be 0 if the leading exponent of numerator is less than the leading exponent of the denominator. It's going to be the ratio between leading coefficients if the degree of the numerator and degree of the denominator are the same. That's the leading exponent equal to the leading exponent. Then it's either plus or minus infinity if the degree of the numerator is bigger than degree of the denominator. So I'm going to explain this a little bit using these two and the other part, because that helps understand how these limits work. The other thing I want you to notice is these limits are both of the form infinity over infinity, and so the form were indeterminate, and we have to do something about it to make it determinate, right? And so that's the other discussion. These two are going to help us do something about an indeterminate form. So why are these why is this formula working? Let's try to do some tricks and convert things to so that we can use the two formulas. In here, we start with, first of all, don't forget these are forms infinity over infinity, so I have to do something, and this is the trick. So we start with factoring out the highest x to power highest exponent on top and bottom. And so see, this is a n x to the power n, then the next one is a minus 1 x to the power n minus 1, and so I will have a n minus 1 over x, and it goes on, and then add a 0 over x to the power n. And then x goes to plus minus infinity. And then the denominator, I factor out x to the power m. Again, this time it's b m plus, this one is b m minus 1. X to power m minus 1, so we end up with b m minus 1 over x plus all the way to b 0 over x to the power m. Now, and so one thing is that now I can clean up these factors. Let's write it as, bring this up, add the exponent becomes negative, and then we'll have a n plus a n minus 1 over a plus a 0 over x to the power n. Same thing in the bottom, b 0 over x to the power m. Now, as x goes to plus and minus infinity, we have to pay attention that we can use either of these because these are polynomials again, and to say that all these terms are gonna, again, I'm gonna use the fact that I can bring the limits in. For the numerator and denominator, if the denominator is not, the limit of the denominator is non-zero, I can do that and basically use a product rule up there and finish this up. But all these terms that are over here, they're all going to go 0 when I bring the limits in. And so we end up with basically a n over bn times the limit of the, so this would be a n over bm times the limit of x to the power n minus m plus minus infinity. And here, if n is less than m, then that means that x to the power negative, that means that is one of those, actually one of these two, and so it goes to 0. It gives 0. If n is equal to m, this becomes 1. Limit of 1 is 1, so the limit is going to be equal to a n over bm, which is the coefficient. Is n bigger than m, then this is going to be x to the power positive, and therefore as x goes to positive or negative infinity, it's going to be plus minus infinity in times depending on the coefficient and that exponent. So you have to kind of calculate which one is true. And so that's how these limits work. And the next is we want to discuss similar type, this time not rational but quotient functions, and see what. Let's example 1, calculate horizontal asymptote. The first part is find the limit as x approaches in positive infinity of square root of 3 plus 9x to the power 6 over 1 minus 2x to the power 3. So first thing to notice, this form is again infinity over infinity, right? If I plug in infinity, I get infinity over infinity. Now, one other thing that I notice is that even though I have a square root, the highest power is 6 and highest power down here is 3. So maybe they simplify. To simplify, I should factor x to the power 6. So the first step is factoring x to power 6 under the square root. And then x to the power 3 in the bottom. And then if I take the x to the power 6 out, and if the exponent is positive, then it becomes x to the power 6 half, which is x to the power 3. And here I know the base is positive. Base is positive. Why? Because x goes to positive infinity. So I can write this as limit x goes to infinity and x to the power 3 over x to the power 3 and times 3 over x to the power 6 plus 9 over 1. So these two simplify. Now I can bring the limits inside the rest. Quotient, that limit of denominator is not 0, and there is a square root, which is a continuous function, so I can bring the limits in, and I get square root of limits as x goes to positive infinity of 3 over x to the power 6 plus limit as x goes to positive infinity of 9, which is 9. And then in here, limit 1 over x to the third as x goes to positive infinity minus 2. And then basically these two are going to be 0. So we end up with square root of 9, which is 3, divided by 2, which is negative 2/3. Y equal to negative 2/3 is the horizontal, one of the horizontal asymptotes. So if you're finding the other horizontal asymptote, if it exists, of this one, we're going to follow the same routine, basically. Factor out it's a form infinity over infinity, and we factor out x to the power 6, ending up with this, and x to the third, ending up with this. And then if I take the x to the 6 outside the square root and write it as x to the third, we have a base that is negative. So how to fix this is to remember that the x to power 2 square root of that is just absolute value of x. So that's how I bring it outside. So it's going to be limit, see, as x goes to negative infinity, that one is negative. And x to the third minus 2. And then remember, x is negative value, so absolute value of x to the third, just look at this one, is going to be negative x to the third. These two simplify, a negative sign is remaining. And so I can write as negative limit x goes to negative infinity. Let's just bring the limit inside. There's those two left, and so I put limit x goes to infinity of 3 over x to the power 6 plus limit of 9 is 9 over limit 1 over x to the power 3. X goes to infinity, negative infinity. Oh, this is negative infinity. Minus 2. And then these two are going to be 0. And that's going to be a negative 2. So you end up with negative square root of 9, which is 3, over negative 2, which is 3/2. So y equal to 3/2 is the other horizontal asymptote for this function. And so let's look at the picture now. So looking at the picture, you see that there's a horizontal asymptote at 3/2 and on the negative infinity side, and horizontal asymptote y equal to negative 3/2 on the positive side in behavior. And another thing to notice is that the function actually crosses the horizontal asymptote and then goes to gets closer and closer to the end behavior. So let's do iClicker question 1. Evaluate the limits of x approaches negative infinity of 2x minus 3 over square root of 16x squared plus 1. I suggest pausing the video, going back to the previous problem and trying to do this all the way by yourself and then looking up the video. So hopefully you paused. And so the first step is to acknowledge this is form infinity over infinity, either positive or negative. What I see is, well, I can put positive, negative. I can see that the degree of the numerator is equal to the basically if I take x squared outside the square root, the highest degree of x in the denominator. So the same song and dance as usual, factor it out. And then x squared, 16 over x squared, plus, 16 plus 1 over x squared under the square root. X goes to negative infinity, so when x squared comes out of the square root, it becomes absolute value of x. So let's do that. X2 minus 3 over x, absolute value of x, 16 plus 1 over x squared. And these two simplify because this is going to be equal to negative x. They simplify, but a negative value, negative sign remains. So it would be limit x goes to negative infinity, negative 2 minus 3 over x over 16 plus 1 over x squared. Now bring the limit in, and it would be negative, limit of 2 is 2, minus limit x goes to negative infinity of 3 over x, over limit of 16 is 16. Oh, the square root over here went away. And so it's square root of 16 plus 1 over x squared. And oh, sorry, limit went away also. Limit of 1 over x squared, x goes to negative infinity. These two parts are 0. So what is remaining is negative 2 over square root of 4, which is negative 1/2. Negative 1/2. And that's the answer. Okay, one last thing to notice is that when you're discussing the asymptotes, the horizontal asymptotes, you're discussing the end behavior. And another thing to notice that we discussed along the way, that a function can cross around and pass through the horizontal asymptote. this function and the two horizontal asymptote can be different. One, you saw it in the previous question. This is a little bit more interesting than previous question, because not only it can cross, it can infinitely many times cross the horizontal asymptote. This is one of those functions that actually oscillates about the horizontal asymptote, and so the amplitude oscillation gets smaller and smaller, but it still crosses the horizontal asymptote.